It doesn't. Why not? How is total concentration defined? Right, so it's the inlet pressure of the PBR over R times the inlet temperature of the PBR. And I'm saying that that's equal to the concentration entering the CSTR, meaning that it's also equal to the inlet pressure of the CSTR and the inlet temperature of the CSTR. Because the pressure drop across the CSTR is negligible, and they're all operating at the same temperature. So you get that. You got 5 points for writing down that. And then the only thing that we're missing now is the mole fraction term we got to get rid of. So first, what is this mole fraction? It's just flow rate of A entering the PBR divided by the total flow rate, or the flow rate of all three species. And now I have to relate all of that to the conversion of the CSTR. This is the same that we already had, FA naught times 1 minus the conversion of the CSTR. So I have that twice. What about the flow rate of B? How do I relate that back to the CSTR terms? Can't forget the stoichiometry there. FA naught x CSTR. And of course, I have two of these. One for B and one for C. All right. So the FA naughts all cancel, right? And 1 minus x CSTR plus a half of x plus a half of x is 1. So you just end up with 1 minus x CSTR. So that simplifies nicely. And you substitute, so we have this, we have the total concentration, 2 parts, total concentration of all gases, and then this species. So we substitute all that in, and what you get is FA naught, 1 minus x CSTR, divided by K, 1 minus x CSTR squared, and the total concentration squared. And you can simplify it further. So that's 10 over 7. Or 1.43. Any questions there? All I did is write out the definition of A, and then for each of those, I related it back to the inlet flow rate to the entire system and the conversion within the CSTR. All right, part A was worth, or sorry, that's part B, was worth 10 points. And part C is also worth 10 points. And it says the valve has now been partially fixed. 40% of the gas enters PBR-B. The rest goes to PBR-A. Each PBR has 5 kilograms of catalyst. And it gives you some information that the pressure drop across PBR-A is 20%. You have to figure out how do we get the same conversion in each PBR. Calculate the pressure drop parameter within PBR-B necessary to achieve the identical conversion out of each PBR. And then there's a second part which we'll get to later. All right, so the pressure leaving reactor A divided by the pressure entering reactor A is 0.8. Everybody know how I got that? Okay. So let's set out some equations that are going to help us solve the problem. So now I'm going to use XA to indicate the conversion leaving PBR-A. So I'm kind of taking this as a model of what we had previously from part A of the problem by using that G term again. All right, and XA need to be equal to XB. So what's the ratio then of those two curves? So you get ratio of those two functions. Let's see what cancels. Any questions so far? All right, so what cancels out? Are the rate constants different? No, same temperature. Are the concentrations different? No, it's a split, right? Valves don't change concentrations. What about the conversion terms? Same conversion. Okay, so it's FAO A over FAO B. What's that? Yeah, 0.6, 60% over 0.4, 40%, 1.5, or 3 over 2. Okay. Now, I come back to this part. So I'm done with the flows, I'm done with the conversion. Now all I have to worry about is the pressure drop. So the ratio of the two pressure drop expressions is equal to 1.5. Sorry, I should have put little a and little b here just to be consistent. All right, so that's the function that we had from part A. So like I said, we're going to use that again. And now I'm just writing it in terms of the pressure drop parameter for PBR-A. Do I have any other information? Yes, right? I have the pressure drop across this reactor. And that is equal to that term. And so I can use that to solve for the pressure drop component, or the pressure drop constant for PBR-A. And if you plug in numbers here, you get 1 over 5 kilogram, and then this is 0.8. And so you get 0.072 inverse kilograms. All right, so that's not what we were asked for. They wanted us to know what was alpha B. That's just alpha A. So the whole pressure drop term, G, now I can use this, plug in, and solve for G. And what you get is 4.1 kilograms. And now I know what I need for this one is going to be that divided by 1.5, which is equal to 2.7 kilograms. And finally, if I use this, but now I set it equal to 1 over 2 alpha B